All right, yeah, I'm Xanthe. I'm a PhD student in the group of Nicholas Spalding at ETH. I defended last month. So as discussed over lunch, in scientific terms, I am still a fetus. So I also want to thank the organizers for allowing a fetus like me to speak today, and you for bearing with me at the last talk of the day. So I wanted to discuss an ongoing project of mine on engineering antiferromagnetic domain states through interface chemistry. So a bit of introduction, why we are interested in interfaces. Interfaces in general, but oxide interfaces in particular, are interesting because they show new properties that the bulk compounds don't show. A famous example of this being the two-dimensional electron gas that occurs at the interface of strontium titanate and lithium aluminate as a way to compensate for the difference in layer charges in these two materials. Another possibility is that an interface can be used to tune bulk properties. An example of this being in ferroelectrics, where sometimes the surface determination can set what type of polarization, so which polarization direction is preferred. And the origin of these, both these phenomena is the fact that whenever there is a discontinuity of the bulk properties, the interface somehow wants to compensate for this. Specifically in magnetic materials, there can be interesting couplings across interfaces, for example, because we're combining two ionic species that are not combined in bulk, but also new magnetic interactions, for example, strong de Chalus-Maria interactions when ferromagnetic and materials and heavy metals are combined. The materials I am looking at are two antiferromagnetically ordered materials, chromium-203 and the isostructural iron-203, and they're both in the corundum structure with the same space group. The chromium oxide is an antiferromagnet, easy access below 307 Kelvin, and the iron oxide is a bit more complicated. It first orders with the moments in the plane, which we can see slightly better in a different projection of the unit cell, and then, so that's below the nil temperature, and then in the Morin transition around 263 Kelvin, they reorder to also be easy access. Now, these two ordering patterns are different in the two materials. In the chromium oxide, it's this down, up pattern, whereas in the iron oxide, it's down, up, down, and this has consequences for their symmetry. In the chromium oxide, both time reversal and inversion symmetry are broken, whereas in the iron oxide, only the time reversal symmetry is broken. In both compounds, the time reversal symmetry breaking means that we have two antiferromagnetic domains, 180-degree domains, and we can define them as such, where we defined two different nil vectors for the chromium compound and the iron compound, and so we have two domains, one with the positive and one with the negative nil vector for both of them. The difference in the inversion symmetry has also consequences for their properties. So the chromium oxide, because both time reversal and inversion symmetry are broken, allows for a net linear magnetoelectric effect. And this is actually also the sign of this effect can be related to its two different antiferromagnetic domains, something collaborators and I worked on, and we were able to show that both across DFT calculations and across all the experiments that have been done, there is a clear consensus which domain belongs with which sign of the magnetoelectric effect. The iron oxide compound in this low temperature phase is actually a altermagnet, showing this interesting spin splitting across momentum space in the absence of spin-orbit coupling. And now the question is, if we interface these two materials, how will the interface compensate for the change in order and also the change in properties of these two materials? So to build the interfaces, I will be switching from the primitive unit cell that I've been showing you to the conventional unit cell, which is just 3 times as large. And we will be stacking these conventional unit cells along the z-axis, so along the 0, 0, 1 directions. And we wanted to study atomically sharp interfaces, which the corundum structure allows two types of. One we call the oxygen-separated interface, because the iron oxide and chromium oxide environments are separated by this oxygen layer. And one which we call the mixed metal interface, where we have this buckled layer of chromium and iron ions separating the two environments. And we wanted to study the magnetic ground state. The reason we chose specifically this interface is because it had been studied both and experimentally before, so we know that this interface can actually be grown, but also because it has some interesting electronic properties. There is a band offset, which is dependent on the interface type. So here I show the density of states layer dependent in the interfaces. So where I colored the just chromium oxide density of states blue, the iron oxide densities of states yellow, and the mixed one green. And we see that there's a shift from the top of the valence band that is downwards when we move to the more iron oxide layers, but this shift is smaller in oxygen separated than in a mixed metal environment. And this is nice applications in photocatalysis because it allows for improved photoexcited carrier separation. But the magnetic properties of these interfaces have not been well studied. And I also wanted to mention that it is known that solid solutions of the two materials can show spin spirals. So we were hoping to see some interesting magnetic effects or magnetic textures at this interface. So in order to study that, we made use of an effective Hamiltonian model. As was mentioned already earlier today, usually the Heisenberg exchanges are the dominant factor in magnetic interactions. So we started with a simple model, just having these exchanges in an anisotropy, which we extracted from ab initio calculations, and then used this Hamiltonian to perform Monte Carlo and spin dynamic simulations in the UPSD code. I extracted the magnetic exchanges up to fifth nearest neighbor, which in the corundum structure looks like this, where they're arranged from shortest interatomic distance to longest. The J2 looks shorter, but that's due to the projection. And I used a finite energy difference model where we're comparing the different energies between ferroic ordering and antiferroic ordering to determine the exchanges. And I looked at both chromium-chromium, iron-iron, and chromium-iron exchanges. And we see that the chromium-chromium exchanges are dominated by the first two, whereas the iron exchanges are dominated by the third and fourth, and the chromium-iron exchanges lie somewhere in the middle, also showing that they're of similar order of magnitude so that it's possible for them to compete at the interface. The single ion anisotropy I extracted from the bulk simply by rotating the magnetization axis away from the z-axis, either onto the x-axis for theta equals 0 or onto the y-axis for theta equals 90 degrees. And so we see that there's no in-plane anisotropy at all. There's no theta dependence, but there's a nice sinusoidal phi dependence as expected. And we see the same for the iron oxide, except that here the single ion anisotropy is quite a bit larger. Now, in our spin dynamic simulations, we make larger unit cells starting from our DFT unit cells. And this means for the bulk compounds that we just have a larger chunk. But for our heterostructure, this means that we actually get supercells with 12 layers of each compound. And of course, we simulate only the magnetic ions because the role of the oxygen in facilitating the exchange is completely absorbed in what we extracted from DFT. Now, for the bulk compounds, we see the following. So here I plot the Neal vector as a function of temperature for the chromium oxide. And I plot both the absolute value of the Neal vector as well as the component perpendicular to z and the component parallel to z. And so we see that we match the Neal temperature quite well and that we immediately move into a state where the moments are arranged parallel to the z-axis. In the iron oxide, in this simple model, we see very similar behavior to the chromium oxide, meaning that we don't capture this Moore transition, but we immediately move into the low temperature arrangement where the moments are parallel to Z. If we now look at our interface, we were hoping to see interesting magnetic, interesting properties that weren't there in bulk, but instead we see the other option, that the interface allows us to tune the bulk properties. Specifically, in our oxygen-separated interface, it allows for a specific combination of domains. Specifically, it combines the chromium domain 1, which has a positive nil vector, and the iron oxide domain 2. And we checked also with density functional theory using this unit cell that this is indeed the lowest energy configuration, lower energy than, for example, combining domain 1 of both compounds. For the mixed metal interface, we find a very different magnetic ground state instead. Here, our magnetic unit cell doubles, and we have a ground state that is a combination of both domains of both compounds in this sort of switching pattern, combining the domains with opposite nil vectors. And we can understand this from looking at the local interface environment. If we look at the spins, it prefers the arrangement where the local moments in this buckled layer are arranged ferroically, which requires the switching of the domains in this manner. And so it's exactly the geometry of the interface that sets which exchanges are dominating and so which domain pattern is preferred. We can look also at the time or the temperature dependence of this domain formation, where I will plot the nil vector within the different layers. So averaged over the unit cells within the layers, but kept the average nil vector of each of the 12 layers of the compounds. And so plot that here. So the Z component of the nil vector in the 12 layers of the two compounds, and here also as a color plot. And so we see at 1500 Kelvin, our materials are completely disordered, but as we lower the temperature, first the iron oxide layers order as expected, and they're completely independent. So some of them have positive nil vector, some of them have negative nil vector, but because they are separated by the disordered chromium-203 layers, they order separately. But now, as our chromium oxide layers order, our iron oxide layers switch to match the chromium oxide pattern, so that it ends up in this switching nil vector ground state that we already saw. But now maybe you would say like, okay, so we didn't see nice spin textures at the interface, but maybe this is also because we had such a simple model. So we extended our model by including also the Shalasinski-Maria interactions and the anisotropic, or the two-side anisotropy, such that we have full tensorial exchange, as well as a quartic anisotropy term and the dipole-dipole interactions. This last term we evaluated explicitly. And if we now look at the two singular compounds, we see that for the chromium oxide, very little has changed from the easy model, or for the simple model. But for the iron oxide, we are now also capturing this Moore transition, where we see that first, when we form the antiferromagnetic pattern, we are aligned perpendicular to Z, and then around the experimental Moore transition temperature, we switch to an arrangement parallel to Z. And I wanted to note here that actually the dipole-dipole interactions play a very important role in facilitating this Moore exchange, because they lower the effective anisotropy. So if we consider the energy difference between being perpendicular to Z and being parallel to Z, that for the specific antiferromagnetic arrangement that the iron oxide has, this actually allows for quite a large energy difference. Whereas if we would instead put a ferromagnetic arrangement, this energy difference is much less. Now, in this more complicated model, we can also look at the temperature development of our mixed metal stack again. And now we see something slightly different, where when the iron oxide layers start to order, they instead stay stuck in that state, and the chromium oxide layers have to adapt themselves to this. Which means that, and we've also checked that this still is the ground state, but we now have created a stack that's magnetically unhappy, because the iron oxide layers are no longer able to switch to adapt to the preferred ordering. So to sum up, we find very different to a more realistic, complicated magnetic model. We find that these ground states are more difficult. Iron oxide layers order first, and then switching. Also, we did not see any effects of the Morin transition also in the more complicated magnetic model. And we are quite sure this is because of the slab structure. So as I showed you before, in the bulk, when I just modeled the iron oxide, we had this nice Morin transition. But if I instead model a slab, which is closer to the geometry we had, then we see that this Morin transition is increased in temperature, but also that in general there is more changing in the directionality of the Mel vector. So let me just present an outlook. So we want to change this to also look at different layer thicknesses and just different geometries for maybe just having a single interface. Look at different interface planes, and also more disordered interfaces that may be more realistic of experiment. Another avenue of exploration is to look at spin wave propagation across such interfaces, because of course you're changing from an altermagnetic material to an antiferromagnet. Finally, I would like to thank my supervisor, Nicholas Spalding, and my student Xanthe, and the whole materials theory group, and you guys for your attention.